Okay, so we talk about pretty good privacy, which is basically PGP. So this is a scheme to provide the authenticity and the privacy in the email, electronics mail. So with the explosively growing reliance on electronics mail for every conceivable purpose, there grows a demand of authentication and confidentiality service. So there are basically two schemes available. One is the pretty good privacy PGP, and another one is secure multipurpose internet mail extension, which is basically S/MIME. This is basically extension version of MIME. So the latter is security enhance of the MIME, that S/MIME internet email. For this is the enhance of the MIME internet email format standard based on the technology from the RSA data security. Although both PGP and SMIME are FITF standard track, it appears likely that MIME will emerge as industry standard for commercial and organization use, while PGP will remain the choice for the personal email security for many users, and usually the PGP is available freely. So this is one of the point to become PGP more popular. So let us talk about background of this PGP. So PGP was basically designed by Zimmerman, and it provides a confidentiality and authentication service that can be used for electronics mail and also the file storage applications. The essence of this PGP has done in the Zimmerman done this in the following way. So Zimmerman selected the best cryptographic algorithm as a building block and used integrated those algorithm into the general purpose application that is independent of operating system and the processor, and that is based on a small set of easy use command. Okay, so basically the idea is to choose the best cryptographic algorithm like AES, RSA, hash function, SHA-1. So then we use those and integrate those algorithm into a general purpose application that is independent of the operating system and processor, and that is based on a small set of easy use command. Okay, so made the package and its source code freely available via the internet. So what Zimmerman did, so he made this package freely available over the internet, and enter into the agreement with the company via script and network associated to provide the fully compatible low cost commercial version of the PGP. So there is a commercial version of the PGP which is low cost, but it is the version there is a free version available over the internet. So that's why it became more popular. So it has wide range of applicability from the corporation that wish to select the enforce a standard scheme for encrypting files and messages to individual who wish to communicate securely with other worldwide over the internet. It was not developed by nor it is controlled by any government or standard organization. So it is free, so anybody can put a command on it, anybody can, like a Linux operating system. For this, with an inscriptive destruct on the establishment, this make PGP attractive. In the last few years, commercial version has become available. So now PGP is on an internet standard track RFC 3156. So this is the operation description of the PGP. PGP consists of basically the 5 services. One is authentication, and then next one is confidentiality, another one is compression, then the email compatibility, and then segmentation. So the table 1 shows, this table shows the summary of these services and the algorithm used to implement them. For example, for digital signature we use the digital signature standard or SA, and also we use RSA, and the description, a hash code or the message is created using the SA1. This message digest is encrypted using the DAS or RSA with the sender private key, and this is the digital signature on it. So after applying the hash code, we compress the message into smaller size, and then we encrypt this using the sender secret key. So this is the digital signature on the message. Then the message encryption. In message encryption we use basically a cast IDA or 3 key tuple DAS with Diffie-Hellman or RSA. So this message encrypted using cast 128 or IDA or 3 DAS triple DAS with one time session key is generated by the sender. The session key is encrypted using Diffie-Hellman or RSA with the received public key, and the include this with the message. And then also another functionality is the compression. It is referred as GIF. The message may be compressed or for storage or transmission using GIF. And email compatibility. So this is the algorithm we use, the radix 64 conversion, and then the segmentation we do. This is the one of the service by PGP. So each service is discussed in, so we will discuss the service in more details. So let us talk about authentication service by the PGP. So let us go to this, there is figure. So this is telling us the authentication service of the PGP. So we have a message, so M. So this is the authentication only, there is no confidentiality. So we have a message M, so we apply the hash function on it to compress this message. Then we apply the encryption algorithm. This is the public key encryption, EP. So we apply the encryption algorithm using the using the public key, and then we send it to the, then we compress, then we concatenate with this with M, and then we zip it and send it. And then after receiving this is source and this is destination. After receiving this, we unzip it and we get this whole thing back, and this is basically encrypted version of the this is basically the digital signature. So we are signing the message, we are signing on the hash code of the message using the secret key of the A. So this is the KRA is the secret key of A, and KRB is the private KUB is the private key of B. So KRA is the secret key of KRA is the secret key of A, and KUA is the private key of A. So after doing the unzip, so what we do, we have this H of encrypted the digital signature on this. So we just do the decryption algorithm on this public key decryption algorithm using the public key of A. So it will give back us the M of H of M. Then we have M, so we compute H again. So we compare these two. If this is matching, then the authentication is done. So this is the way we apply the authentication. So let us come back. So that figure illustrates the digital signature service provided by PGP. The hash function is used here is SHA-1, which creates a 160-bit message digest. EP and DP represent the public key encryption or decryption, and the algorithm we use here is RSA or digital signature standard, which is basically use the Elgamal crypto system. And this zip is denoted by this is the compression. Zipping is denoted, we zip the function the folder. So this is the message along with the hash code, and this is denoted by Z in the figure. And this is the due to the strength of RSA, the recipient is assured that only the possessor of the matching private key can generate the signature. And because the strength of the SHA-1, the recipient is assured that no one else could generate the new message that match the hash code, and hence the signature of the original message. So, that is this is the birthday paradox or birthday attacks. This is the collision resistance. So, it is very difficult to generate another function is which is having the same hash function. So, that is the collision resistance. So, this is the first applications, authentication, and this is here is the confidentiality. So, here we have M. So, we apply this Z on it to compress, then we apply then we sign on it, then we apply again this case we use the public key encryption using the public key of B, so that B can decrypt it, and then this combination we are sending to the B, and then upon receiving this, so this has to be decrypt first, and then we get this, and this we again using the decryption algorithm, symmetric decryption algorithm, we get back this, and then we unzip it and get the message. So, this is the confidentiality. Okay. So, this is the another basic service provided PGP is the confidentiality, which is provided by encrypting the message to be transmitted or to be stored locally in the file. So, this PGP is applied to the as a file storage mechanism. So, in both the cases the user has choose the AES or this cast 128-bit IDA or triple trace, or in the 64-bit cypher CFB modes of operation. The symmetric key is used only once and is created as a random number with a required number of bits. It is transmitted along with the message, and it is encrypted using the recipient public key. So, this is the symmetric key encryption, which is encrypted using this KS, and this KS is transmitted, KS is encrypted using the receiver public key and transmitted along with this, so that receiver can able to get this KS, then only receiver after getting this KS, receiver will decrypt this and get the zip message, and then unzip it and get the message in. So, this is the confidentiality. So, this is only the confidentiality. Now, suppose we want both the confidentiality and the authenticity. So, for that what we have to do? So, the sender generate a message and the random number to be used for the as a session key for this message only. So, let us go back to the slide picture. So, this figure is both confidentiality and the authentication. What we are doing here? We have the message, we first apply the hash function on this message, then we are using the public key encryption using this is the digital signature. We are signing, the A is signing on this message, on the hash code of this message, and then we are appending this M with the signed signature signed on the hash code of the message, and then we compressed this zip, and then we do the symmetric key encryption using a randomly generated key, which is KS, and KS need to send to Bob, but KS needs to send to B in order to decrypt it, and this KS is sent to B by encrypting this KS using the public key of B, so that only B can decrypt it. So, this we are just combining and send it to B. So, upon receiving this, B will first decrypt this and get the KS. So, after getting KS, B will just apply the symmetric key decryption and get this, and then apply the unzip, then got this, then we check the this authentication. This is the authentication checking. So, this is the way we both use the public key and private key setup in order to get the both confidentiality and the authenticity. So, this is the both confidentiality and the authenticity. Okay, so this is the so here we use AES or triple dash for the symmetric key encryption, and for the public key encryption we can use RSA, LGML. So, any standard cryptographic this, and session key is used for decryption the message, and which is randomly chosen by the sender A. As mentioned before, public key encryption is a lot more computationally intensive than the symmetric key encryption. So, public key encryption is more costly than the symmetric key encryption, because public key encryption involves, if we use the RSA, it involves say m to the power e, or if it is L-gamma, it involves the discrete some powering to the power some index. So, it is very much expensive. On the other hand, the symmetric key encryption, we use the S box, we use permutation, we use the XOR. So, those are very fast operation. But this is not much secure than the public key encryption, but public key encryption is more expensive. So, for this reason, both form of use the public key encryption solve the key distribution problem. So, this is the confidentiality and the authentication, which we described just now in figure 2c. Okay, so this we discussed, this sequence is preferably the opposite encryption the message. We can have some other variant of it. Okay, now let us talk about the compression service. This is also another service of PGP. As a default, PGP compress the message after applying the signature, but before the encryption. So, the JIP, this has a benefit of saving space, both email transmission and for file storage, because if we can compress before the encryption, because encryption, if we use the public key encryption is expensive. So, if we have very long message, say 120 bit message. So, if we just use the public key encryption on the 120 bit message, so if we use RSA, we have to do m to the power e. So, it is very expensive. So, instead of that, if we can compress this message to a fixed length, say just 128 bit. So, 124 bit to 128 bit, then if we can apply the RSA, this expensive operation exponentiation. So, that is why we just apply the compression function, and it also has the benefit of saving the storage for file storing. The placement of the compression algorithm indicating by Z for compression and Z inverse for decompression, as we have discussed. The signature is generated before the compression for two reasons, because it is preferable to sign an uncompressed message. So, it is free of the need of the compression algorithm for later verification, and different version of PGP produce different compression form. So, applying the hash function and the signature of the compression would constrain all the PGP implementation to the same version of the compression algorithm. So, that is why we apply the compression, we generate the signature before the compression, and the message encryption is applied after the compression to strengthen the cryptographic security, because the compressed message has a less redundancy than the original plain text. Cryptanalysis is more difficult, and as well as the computationally it is faster, because if we have less size compressed message, then exponentiation is much more faster. Okay, then next service of PGP is called email compatibility. So, many electronics mail system only permit the use of block consisting of ASCII text. Okay. So, when PGP is used, at least part of the block to be transmitted is encrypted. This basically produce a sequence of arbitrary binary words which some mail system won't accept. So, to accommodate this restriction, PGP use an algorithm known as radix 64, which maps 64 bit of a binary data into 8 bit ASCII character, because in many email system they are compatible with the ASCII text, they are not compatible with the binary data. So, for that we have a algorithm which is called radix 64, because we are doing the encryption, decryption. So, after that we are getting the binary bits 0-1 bits. So, this radix 64 will convert this, take these binary bits to the ASCII characters. Okay, but unfortunately this expand the message by 33%. However, with the compression algorithm, the overall compression will be above 1/3 of in general. Okay, so another functionality of this PGP is segmentation. So email facilitated are often restricted to the maximum message length. For example, many of the facilitated accessible throughout the internet impose a maximum length of octet, 50,000 octet. Any message longer than that must be broken off into a smaller segment. So we need to do the segmentation, each of which is mailed separately. To accommodate this restriction, PGP automatically subdivides a message that is too large into a segment and that are small enough to send via email. So this is the segmentation is required because of the size restriction of the message to be sent. So this is one service. The segmentation is done after all the other processing, including the radix 64 conversation. Thus the session key component and the digital component appear only once at the beginning of the first segment. So at the receiving end, PGP must strip off all email headers and reassemble the entire original block before performing the step illustrated in figure 3. So this is the step it is performing. Suppose this is the X is the file which need to be sent. So is the signature is required? If no, then we go for the compression. If yes, we generate the signature and we put the signature and the original message, and then we go for the compression, because signature is done before compression. And then after compression we ask for the confidentiality. If we need the confidentiality of the message, then we go for the this encryption, and then otherwise we go for the direct this, and then we convert this into ASCII, because email system is compatible with the ASCII. So this is the generic transmission diagram from A, and from B. So recipient, what recipient is doing? So recipient is getting this ASCII and recipient is converting from ASCII to binary by this radix 64, the reverse, I mean ASCII to binary. Then the confidentiality is required. If it was used, then decrypt it and get back here, and then again apply the decompose Z inverse and get it, and whether it was signed. If it is signed, then the signature is checked, otherwise this is the file X which is sent. Okay, so now talk about cryptographic key and key ring. So PGP make use of 4 types of key. One is one time session symmetric key, that is the KS, which is randomly chosen and which need to be sent to the receiver. And second one is public key, that public key and private key pair, and the private key, and the parts based symmetric key. So these 3 separate requirement can be identified with respect to these 3 keys. A means of generating the unpredictable session key is needed, because session key is chosen by A, that KS. So KS is chosen randomly by A, and we would like to allow the user to have the multiple private key public key pair. As a result, there is not a one-to-one corresponding between users and his public key. Thus some means is needed for identifying the particular key. So each PGP entry must maintain a file for its own public and private key pairs, as well as a file of public key of correspond. Okay, so now the question is how one can generate the session key. So each session key is associated with a single message. So once that session is gone, we destroy the key. So this session key is basically for a specific message, for the specific session. So once that session is gone, we will no more use that key. So that is the call of session key. So each session key associated with a single message, and it is used only for the purpose of the encryption and decryption for that particular message. Recall the message encryption is done with the symmetric key. So we use the KS, and this is maybe 128-bit random key if we are using AES. Okay. So, now the input of a random number generator consists of 128 bit key, because if you are using the AES needs 128 bit key. Using CFB modes, 264 bit ciphertext block are produced and concatenated to the form of 64 bit session key. So, this is the session key generation. Then the key identifier, how we can identify the key. As maintained, it is possible to have more than one public key private key pair. Each one therefore need to have an identity of some kind. The ID is associated with the public key consists of at least significant 64 bits. So, this is maybe we can use the ID is associated with the public key, and that is the ID of the public key UA. So, KU, this is the public key of A. So, mod 2 to the power 64. So, we want to make this, each of this key is 64 bit. So, this is the sufficient length, because this is the public key encryption. So, this we use here. So, this is the general format of PGP message. So, this is the content. So, this is the session key is kept here, and this is the ID of the recipient, and this is the timestamp and key ID of the sender, and this is the digital, this is the signature part, and this is the message part where which contain the file name, timestamp and the data, and this is the encryption of the KUB. KUB means the public key of B. So, like this. So, this part we usually give, and this part is EKS. We encrypt this part. We encrypt this part using the session key. This is the symmetric key encryption, and then we apply this RX64 to convert this into the ASCII. Okay. So, then we have the key rings. So, the key IDs are critical to operation of PGP. So, this is the general structure of private and the public key rings. So, here we have a timestamp, we have this key IDs, this is the public key, and the encrypted private key, and this is the user ID, and this is basically private key rings, and this is the public key rings. So, this is basically key rings used in PGP. This we have discussed: timestamp, key ID, public key, private key, and the user ID is used. So, a free version of this PGP is available here. So, one can download this for their own use, and this is the PGP message generation structure which we have discussed. So, this is basically ID is giving us the encrypted the key ring is here. So, we get the ID, then the message is hashed, then we apply the encryption. This is the public key encryption, and this public key we are getting from the from here, and then after encrypting we are sending to the BOP to the receiver B, and B is doing the same thing. B has a public key ring. From there, upon get public, this is the ID of B and getting the public key and doing the same process. So, this is the encrypted signature plus the message, and then we are doing the output. So, this is the general message generation of the PGP. Thank you.